Our video on ratio and root tests, only we're actually only going to do the ratio test. The root test is not on the exam, and we really don't have a reason to cover it, so we're not going to do that. So the ratio test is super important because it is a very easy test, and it's definitely one that we can use, and it's probably like the one I would choose first, and then for lots of different cases. Okay, so we'll kind of see when we would choose it versus other things. So this is the ratio test. So if we have a series that has non-zero terms, if we take the limit as we go to infinity of the n plus 1 term over the nth term, so we are simply looking at the next term, so the n plus 1 term divided by the nth term. If that ratio, as you take the limit, so you have to take the limit as n goes to infinity, as we go to infinity, if that ratio is less than 1, then the series will converge. So remember, convergence often relies on how fast we go to 0. So if you are going to 0, that would mean that this term must be smaller because it's the next term. And so if you have a smaller number over a number over a bigger number, a number that's bigger than it, then of course it should be less than 1. Okay, so that's the idea. So we compare it generically, though, can't put numbers in. We just generically compare the n plus 1 term to the nth term, do the limit. As long as that's less than 1, we're good, it converges. If it's greater than 1, it diverges, okay? So greater than 1, definitely no good, diverges. If it equals 1, the test is inconclusive. And that's the unfortunate part about some of these tests. We can't always use them. So even though this would be our preferred test, often, sometimes it's inconclusive, and so we'll have to try something else. Okay, so let's do an example. So here we have, and I'm sorry the cancel's in the middle, it's on my computer, I don't know what that's for. So anyway, determine whether the following converge or diverge. Okay, so if I was just asked to do it, nobody told me what type of series it was or anything, or what test would be best, or it wasn't on the assignment that's on ratio test, I would just say to myself, okay, this goes for the ratio test because of the n factorial. So definitely, if you see a factorial, then you are definitely going to decide, hey, this is the ratio test. Okay, so all we do to do the ratio test is we take the limit as n goes to infinity of the absolute value of the n plus 1 term over the nth term, but just like on the limit comparison test, that means do the n plus 1 term times the nth term flipped over, right? Invert and multiply if you're dividing, okay? And then we just evaluate this limit. So first, to do the limit, before we can do the limit, we need to simplify what we have here, okay? So 2 to the n plus 1 over 2 to the n. Lots of things you can choose to think about here, okay? So you can subtract exponents because you're dividing. So n plus 1 minus n would give me a 1, so I'd have 2 to the first. Another way to think about it is 2 raised to a power means I'm multiplying by itself over and over and over again. So the top one, I'm doing it one more time. So that means there is 1, 2 left here. Okay? So however you want to think about it, there's 2 times 2 times 2 times 2 times 2, one more time on the top than there is on the bottom. So they'll all cancel except for the one on the top. Then n factorial and n plus 1 factorial. So what we need to remember is that n plus 1 factorial means n plus 1 times n minus 1 times and so on times 3 times 2 times 1. But remember that n factorial means n times n minus 1, etc., etc., etc. So this is really n plus 1 times n factorial. So that means the n factorial will go away, and I will be left with just n plus 1. Now, I like to not just, some students think, well, just mark off the factorial and so on, but I really like to rewrite it. That just really leads to less mistakes, okay? So what I'm actually taking the limit of is the absolute value of 2 over n plus 1. So now I do the limit as we go to infinity. So this is normal limits. The bottom's going to be infinity, so this limit is 0. Now the criteria is I need the limit to be less than 1. So then you need to show that. This is less than 1. Thus, and then always write the original series. Converges by the ratio test. Okay, so always state the conclusion and by which test. And again, I always write the series again. Don't say it converges or anything like that. It's always better just to write it down, then you're very clear. Okay, so let's do the next one. So again, even if I was not on the lesson that said, hey, it's ratio test, the factorial is what would tell me I'm going to try the ratio test. So I'm going to do the limit as n goes to infinity of the absolute value of the n plus 1 term. So n plus 1 plus 1 is n plus 2 factorial over 3 to the n plus 1. I simply replace the n's with n plus 1 times the nth term flipped over, because again, what you're technically doing is dividing by the nth term. So dividing is same as invert and multiply. Then again, reduce everything carefully. So 3 to the n over 3 to the n plus 1 means there's one more 3 down here in the bottom. That's all being multiplied, so I'm left with a 3. N plus 2 factorial would be, again, thinking over here to the side, n plus 2 factorial means n plus 2 times n plus 1 times n, etc., but that's just n factorial. So that means this and this will cancel, and this becomes n plus 2. So we're going to end up with the limit as n goes to infinity of n, absolute value of n plus 2 over 3. So if we do evaluate that limit, now you got infinity on the top, so you get infinity. And infinity is certainly greater than 1. So thus, again, original series, write the whole thing down. Diverges by the ratio test. So it's really a pretty simple test. It's just unfortunate if it doesn't work, okay? So as long as it works, it's a great test. It will not work if you have rational expressions, because you're not going to be able to simplify anything. You're not going to be able to tell that. If you've got rational expressions, polynomials over polynomials, that's when we use limit comparison test, okay, which is different. That's when you compare it to something that you know converges or diverges based on what you think. But the ratio test will be really, really useful if you have exponentials, if you have factorials, all of those things. Okay, so here is going to be one that's inconclusive. So let's go ahead and, again, just look at it and say, okay, I'm going to try the ratio test. So we're going to do the limit as n goes to infinity of absolute value of the n plus 1 term. So again, you're replacing the n's with n plus 1, and then divided by the nth term, which means flip over the nth term. So this ends up being the limit as n goes to infinity of, so now we're going to have to kind of figure out what we have left here. Well, for this one, you're going to basically just have two separate things that you can't really do a whole lot with. So you're going to have, but remember with limits, you can do them separate. So I'm going to put the n over n plus 1, the third roots. Okay, so I'm putting this part, I'm putting in one limit. times the limit as n goes to infinity of the n plus 1 over n, because we want to consider them separately. Now, you don't have to physically write this. You could just consider them both separate, okay? But if I do both of these, I end up with, remembering how we do our limits, this is third root of 1, and this is a 1, because I'm going to infinity, so this limit actually equals 1, okay? So you can't conclude anything for this. So ratio test inconclusive. Now, that doesn't mean we can't solve it. It just means that I can't use this test to do it, okay? So I would have to use a different test. Well, this one's pretty simple to see what test I would use. So let's just go ahead and consider what I would have normally done right from the beginning. Is as soon as I looked at this, I would have said, hey, this is just, the bottom is actually just n to the 1/3, right? Because it's third root of n. So you can just simply make this a p series where you have 1 over n to the, or actually not, I mean, you can even look at it easier. It's just going to be n to the 2/3, because it's n to the first minus to the 1 minus 1/3. And if you do this limit of the inside, remember the nth term divergence test is kind of the first thing we usually do. This limit is infinity, so diverges by nth term divergence test. Infinity, which is not 0, so diverges by nth term divergence test. So we didn't even, in a normal world, I would have just said, I'm not even doing the ratio test, but of course we were doing it to show you that that sometimes is inconclusive. But remember that the nth term divergence test really should be the first thing that you start with. Now, the next test listed here again is the root test, but we're not going to do the root test because it's not required, and so we don't need to add another thing for us to do, especially given everything that's kind of going on. So this page is really important, though. This is strategies for choosing a test, okay? So we have all these different tests. We don't consider, of course, remember that telescoping is not on the AP test, and neither is the root test. So those are two that you will not see, okay? But definitely the very first thing I would always look at is, hey, is this just geometric? Is it a p-series? Is it alternating? Because I have very specific tests for those situations. So we definitely want to start there. If it's geometric, if it's a p-series, definitely if it's alternating, I have ways to handle that. Then what I would actually do second is I would actually second do the nth term test. Because if I check that, like first I just say, okay, it's geometric or it's not or something. If I can't determine anything really quickly about alternating or anything, then I go ahead and do the nth term divergence test. Because if I don't get the limit going to 0, I'm done. It diverges by the nth term test. Then I might check to see if there's a comparison that I could do. Mainly, we would do comparison tests if we have rational functions. Okay, so if it's some kind of rational function of some kind, then I might do that. And then number 4, last thing I would choose, hey, is it something that works for integral test or ratio test? Now, for integral test, my mind would be, is it easy to integrate? Like when I look at the integral test, I wouldn't probably consider that unless I look at that and go, hey, that's just whatever. You know, I know how to integrate that. Then I make sure it's decreasing, continuous, and positive, and then I can do that test. Ratio test, if you have factorials. That should really just be your first. As soon as you see a factorial, jump right to the ratio test. That's how I would handle that. So be sure you're writing some of those things down as you discuss stuff. Okay, so now what we're going to do is we're going to look at these different ones and we're going to write down what tests we think we should use, typing with those guidelines. So if we look at A, you should immediately notice that this is geometric. Okay, so again, first thing I do is say, hey, this is geometric. And so I would know exactly what to do to handle it. I know that the absolute value of R equals pi over 3. which is greater than 1, because pi is 3.14 something. And so we're definitely greater than 1. And for geometric, that means that the series diverges. Okay, and remember, you don't have to say by the geometric series test because you said it was geometric first. So if I identify, hey, it's geometric, absolute value of r is pi over 3 is definitely more than 1, thus it diverges. Okay, and that's it. Because remember, with geometric, you keep multiplying by a number bigger than 1, you're just going to keep getting terms that get bigger and bigger and bigger, and bigger is not good for convergence, so that's going to diverge. B is an example of a rational expression. So I would probably use the limit comparison test. Remember that the direct comparison test is the last thing I would ever choose, wouldn't even hardly ever look at it, probably never going to need it, okay? So I would use the limit comparison test. And again, my clue, and so something you might write for yourself, my clue that this would be a good choice is that it's a rational function, okay? It's a polynomial over a polynomial. So what I would do is I would compare it to, and remember you compare it to, you basically get rid of all the numbers and things and just look at this. So I would compare it to 1 over n, which is a divergence harmonic series. So I know that diverges, so then I would do my limit comparison, which is simply do the limit as n goes to infinity of the one that you're looking at divided by the one I'm comparing it to, but remember divided by means you flip it, invert and multiply, and so this is going to be this limit. And this limit is going to be 1/4, which is finite and positive. And that's what we needed for them to do the same thing, okay? So since the limit was finite and positive, then I would say thus, and then again, always write the original series. This series diverges by limit comparison test. Okay, so that's how I would do that. Okay, let's look at the next one. So first thing I might look at is say, hey, that's a rational expression, but very quickly I should immediately notice that my limit is not going to be 0. So that's a quick one. Limit as n goes to infinity, n plus 1 over 4n plus 1 equals 1/4, which is not 0, right? Because got to be 0 to have any chance to converge. Thus, diverges by nth term divergence test. Okay. All right, let's go to the next one. So I see e over e to the n squared. Now that one's a little more difficult to figure out what to do right away. But if you think about something like the ratio test, there's no way I'd be able to cancel anything out, so that's not going to really work. I'm not going to want to do a comparison of any kind because I have no idea what to compare it to. So this one is actually going to be the integral test. Okay, so what I will do is I will let f of x equal actually x e to the minus x squared, because I really want that power to be at the top, or that exponential at the top. And then in that case, I can actually integrate it, okay? So I need to say that, I'm going to just put comma, this is decreasing, continuous, and positive. And at this point, I wouldn't worry about having to show those things as long as you're fairly sure they're true, because definitely the bottom is way bigger than the top, so it's certainly going to be decreasing. There's no zeros in the bottom, so it's continuous, and all the numbers you're plugging in are positive, and everything lends it to be positive. So that's very valid, okay? I don't need to prove it, I just need to say it though. So since it's decreasing, continuous, and positive, I'm going to let f equal that, and then I'm going to integrate from 1 to infinity of x e to the minus x squared dx. Now this is going to be a simple u substitution in order to do that. I'm not going to write out the u substitution part because I don't really need to. It's a pretty simple u substitution. I know that if I let u equal the minus x squared, then I will have du equaling negative 2x dx. So I fix it, which means I got to put a negative 1/2 on the outside. And so now I'm going to do a couple of things at once. If you need some review on that, then you go back and review u substitution, go watch some videos, do some extra work on that, okay? So I'm going to go ahead and change the things that I need to in order to do this limit. Okay, so remember we let b go to infinity, 1 to b, and then I'm going to leave it negative 2x e to the minus x squared dx. I don't want to put the u in there because the limits of integration are for x, and I don't want to change that when I have an infinite limit like that. So this is simply going to be negative 1/2 times the limit as b goes to infinity. And then really, just remember, this was u and this is du. So I have e to the u du. Well, when you integrate that, you're just going to get e to the u. But instead of u, I need to write the negative x squared. And then I'm going from 1 to b, which is going to be negative 1/2. Whoa, negative 1/2. Go ahead and extend the page so it doesn't keep bouncing. And then I still can't do the limit yet because remember I have to substitute. So I'm going to have e to the minus b squared minus e to the minus 1. And so that's negative 1/2 times. Now if I do this limit, I'm going to get e to the minus infinity, because when I put infinity here, there's already a minus sign. So it's e to the minus infinity, which is 0, minus, so I can even put 0 if I want, minus e to the negative 1. So that's going to end up being 1 over 2e. And that's my answer, which means the integral converges. And since the integral converges, thus the series n over e to the n squared converges also. Because remember, they do the same thing, okay, by the integral test. Okay, the integral test is definitely not my favorite, but sometimes you have to use it because it's definitely longer than some of them. Okay, so as soon as I look at E, as soon as I look at this question, I should immediately know, hey, it's alternating. There's your alternator right there. So this is definitely an alternating series. And so I want to go through the process of using the alternating series test. Okay, so this is an alternating series. And remember, for alternating series, I just have to show that the n plus 1 term is greater than question mark, or sorry, not greater than, the n plus 1 term is less than the nth term. So this is my question mark because I need to figure that out. Well, it's very, very easy to see that that's going to be the case because the left-hand side is the same, except it has plus 4 on the bottom because you'll have plus 3 right here plus another 1. So instead of 3n plus 1, it'll be 3n plus 4, which makes it bigger on the bottom. Numerators are the same. So this is true for n greater than or equal to 1, which is, again, all I care about. It's doing that. And so it is decreasing, and the limit as n goes to infinity of the 2 over 3n plus 1 equals 0. Thus, and that's all, remember, all we had to show for the alternating series, negative 1 to the n times 2 over 3n plus 1 converges by alternating series test. Okay. All right, let's look at the next one. This one is actually the one we're not going to do. This would be the root test, so we don't need that. So just skip that. We're not going to have one that looks like that. And then this one, you should immediately say to yourself, there's a factorial in it, so I'm going to do the ratio test. Okay, so immediate factorial ratio test. So I'm going to do the limit as n goes to infinity of the n plus 1 term, and I got to do absolute value, over the nth term, which again means invert and multiply. So this is going to simplify to n plus 1 over 3, absolute value. This limit is definitely not less than 1. It's infinity, which is greater than 1. Thus, my series diverges by the ratio test. Okay, then the back of your note packet has a table that has the different tests and different things going on. So what I would do is I would just cross off telescoping, because even though it's something you need to know possibly in the future, it's not on the AP test. So right now I don't want to be considering it. I don't want to think about it as something when I'm looking at my tests. And same thing with the root test. I would cross that off. Notice that the very last thing that's written, the last two are direct comparison and limit comparison. I would make notes next to all these, like direct comparison would be my last choice, probably never going to use it. Okay, so I would make some notes about that. Limit comparison, remember, very often when you see rational functions, limit comparison is going to be what you use. Ratio test, you're going to think of the ratio test definitely when you see factorials. Alternating series is obvious, P series, geometric, and so on. Okay, so make some notes next to that, and then that's a very good chart to have to help you organize all of those. So that is everything on the ratio test and kind of a summary of everything about the test that we've done.